Hello students, we'll discuss today about force on a moving charge when it is in a uniform magnetic field. Okay, so here you can see that, so let along the y-axis the uniform magnetic field B is acting and a charge Q is moving along this direction so that it is making an angle theta with the magnetic field. Okay, so we have to find out what is the force acting on that charge. So here what I have written here, so let Q is the positive charge which is moving with velocity V by making an angle theta with the field B. Okay. Now experimentally it is found that that charge which is making an angle theta with the field, it is going to experience a force, and that force is directly proportional to the charge Q. It is directly proportional to the magnitude of the field, that is B. It is directly proportional to the component of velocity that is perpendicular to the magnetic field. That means you can see here V is making theta with this magnetic field V, and its components, one component act along x-axis and other component will act along the y-axis. The component which will be perpendicular to the magnetic field, this component will be V sine theta component. So that's why it is depending on this V sine theta component. Now if we combine all this, it can be equal to what? F directly proportional to QVB sine theta, or we can write down F is equals to a constant K QVB sine theta. Okay, now here experimentally it was calculated the K value to be equals to 1. So that's why what will be F value? F will be equals to QVB sine theta. So this is the magnitude of the force experienced by the charge particle while it is moving with velocity V by making an angle theta with the magnetic field. Now the same expression, if I write it in vector form, F will be equals to what? This will be QV cross B. The expression can be written as what? QV cross B. Okay, so here one thing you can see, because there is a term that is VB sine theta, so in place of that, so you have written that this is a cross product of what? V cross B. So this is the vector form of this force. Now here we'll see that how to find what is the magnitude at different angles or different cases here. Now we'll discuss about some special cases here. Okay, so this was the expression what we got, F equals to QVB sine theta. Now here under this case 1, that is if charge is stationary. Charge is stationary, that means what? What is the velocity of the charge? V will be equals to 0. Now if V 0, in that expression F equals to QVB sine theta. Now if V is 0, so what is the force? In that case F will be equals to 0. So that means if a charge is stationary or it is at rest in a uniform magnetic field, it's not going to experience any force from the field. Okay, so this is important, you remember. Now second case, if theta is either 0 or 180 degree. So that means if the charge, this is the direction of the charge which is moving. So if the charge is making angle what 0 degree, that means if it is moving parallel to the field, or it is making 180, that means it is moving anti-parallel to the field. That means if charge is moving parallel or anti-parallel to the field. Okay, if the charge is moving parallel or anti-parallel to the field, in that case you can see here what is sine 0? Sine 0 equals to 0, even sine 180 is 0. So in that case F equals to 0. So here since sine 0 degree equals to 0, even sine 180 degree equals to also 0. So that's where the force acting is 0. So that means in both the cases, if the charge is moving parallel to the field or it is moving anti-parallel to the field, in both the cases what? The force is equals to 0. Now the third case, if theta equals to 90 degree. If theta equals to what? 90 degree. So that means what is sine 90? Sine 90 equals to 1. So in that case, F will be having its maximum value, that equals to what? QVB. Because here sine 90 equals to how much? Sine 90 equals to what? 1. Okay. So since sine 90 value equals to 1, so F will be the maximum value, and that is nothing but your QVB. Okay. So this is how we have calculated, or we have seen the different cases under which we can now say that in which case the charge is going to experience a force and which case it's not going to experience any force. Now from that expression we got F equals to QVB sine theta. From this expression we can find out what is the SI unit for the magnetic field. Now look at here, F equals to QVB sine theta. From your B's formula will be F by QV sine theta. Okay, so this formula can be used to find out what is the SI unit of magnetic field. Look at here, in SI system, force unit is what? Newton. What is charge unit? Charge unit is Coulomb. And what is velocity's unit? That is meter per second, and sine theta has no unit. So that means here if we'll combine all, so that will be giving you B's unit. So magnetic field's unit will be, so that means all you can say, previously we have already discussed what is magnetic field's SI unit, that is Tesla. So that means magnetic field B will be Tesla, that is 1 Tesla can be written as what? 1 Newton divided by here what? 1 Coulomb into 1 meter per second. Or it is equivalent to write, this is 1 Newton. Here you can see this is 1 Coulomb per second I can write, and this is 1 meter. And what is Coulomb per second? Coulomb is charge unit, and S, that is second, that is times unit. So charge per unit time, Q by T. So whose formula? That is current. And what is current's SI unit? That is ampere. So that means in place of Coulomb per second I can write that is ampere. So that is 1 Newton is, 1 Newton, and this is 1 Coulomb per second is 1 ampere, and this is 1 meter. Okay, so this is the relation between Tesla and this Newton ampere meter. 1 Tesla is nothing but here 1 Newton per ampere meter. 1 Tesla equals to 1 Newton per ampere meter. Okay. So what is the force experienced by charged particle while it is moving in a magnetic field? So we came to know F equals to what? QVB sine theta. That is the magnitude of the force, that is QVB sine theta. But to find the direction, so we'll go for its vector relation, that is F equals to, or vector form, that is F equals to Q V cross B. Okay. So here we can find its direction by different rules here. One of the rule is here, that is which is used in the cross product method here, that is called as your right hand screw rule. Right hand screw rule. So that rule you must be knowing. What is right hand screw rule? So right hand screw rule says what? If you just hold a right handed screw, okay, and you just turn, means on the plane containing V and B, where the right handed screw you have to keep on the plane containing V and B, and if you have to turn your screw from what? First vector to second vector. First vector is V, second vector is B. So first vector to second vector. So the direction in which the screw will get advanced, that will be the direction of what? The force. Okay. So that means this force will be always perpendicular to the plane containing V and B. To V and B. So it will be always perpendicular to that. Okay. So this is right hand screw rule. So that is known to you. There is another rule I'll say, that is called as your Fleming's rule. Fleming's left hand rule. Fleming's left hand rule. Okay, but this Fleming's left hand rule can only be used if theta equals to 90 degree. What is theta 90? This theta. That means the angle between that velocity vector and the magnetic field, if it is 90 degree, that means you can say if the charge particle is moving at 90 degree to the magnetic field, in that case you can use this Fleming's left hand rule to find the direction of the force. So what is the statement of this Fleming's left hand rule? So you can see that you have to stretch the 3 fingers of your left hand. Which 3 fingers? Thumb, the forefinger or the first finger, and the middle or central finger. Okay, in mutually perpendicular direction. You have to stretch it in mutually perpendicular directions. You can see here, mutually perpendicular directions. Then if the first finger points the direction of the magnetic field, okay, the first finger points the direction of the magnetic field, then this central finger points the direction of the flow of current. Flow of current means what? That is the direction in which the positive charge moves. That is important, you remember. So the flow of current. Then the thumb will give you the direction of the force. Okay, so that means force direction will be given by your thumb. Understood what I said here? The first finger points the direction of the magnetic field. The central finger points the direction of the flow of current, or you can say the flow of positive charges, and then the thumb gives you the direction of force. That is what the Fleming's left hand rule. That can be also used to find out what is the direction of the force. Okay. So next we'll discuss about what is Lorentz force. And what is Lorentz force? Lorentz force is the what? That is the sum total of the force due to electric field and magnetic field. And when this force can be calculated, that means when a charge is moving, both means under both the fields, okay, that means electric field and magnetic field simultaneously acting at a particular region. In that case, what is the total sum, or you can say the total force experienced by the charge? That is actually called as what? That is the force. So that means here, that is called as your Lorentz force. So that means when a charge is moving in a region where both electric field and magnetic field is acting, then the total force experienced by the charge is called Lorentz force. Okay, that is what we are discussing, that is Lorentz force. So that's it. Here Lorentz force is the vector sum of what? That is force due to electric field, plus force due to magnetic field. Force due to electric field plus force due to magnetic field. That means we can write F equals to Fe plus Fm, where Fe stands for the force due to electric field and Fm stands for the force due to magnetic field. And previously we know what is the force due to electric field when a charge is in an uniform electric field. What is the force experience? That's equals to what? QE. What is E here? So that means if I am writing in vector form, so here F will be equals to QE plus here Fm, that is the force due to magnetic field, and what is the formula? That is QV cross B. Okay, now look at here, this already we have discussed what is the force due to magnetic field. Now here you can see, though this is not new to you, you know what is the formula of the force experienced by the charge in a uniform electric field. What is the formula? QE. What is E stands for? This capital E stands for the what? That is the magnitude of the electric field. Now here you can see that in this case, so this you can see that when a charge is in a uniform electric field, so in whether the charge is at rest or it is in motion, in every case it's going to experience a force. It's not like your magnetic force. But in case of uniform magnetic field, when we are keeping a charge, what happens here? If the charge is in motion, in that case only we are going to get a what force? But if the charge is stationary, in that case we are not going to get the force. Okay, even other cases also we have discussed. So that means here this is the formula which is showing. So here F is the total force which is called as the Lorentz force, which is the sum total of the force due to electric field, which is QE, and force due to magnetic field.